Я. Спасибо. Сейчас какой-то звук еще раздается. Так должно быть. Хорошо. Okay. So, last time we have also introduced some important, deep concepts. So let's go over them once again. So we started with the big group, symplectic group of four-dimensional vector space. Like this. So this was two-dimensional with symplectic form. And this was the quadratic extension with symmetric bilinear form. Xy is xy bar plus x bar y, where x bar is x to the power q, Frobenius. Okay, so the tensor product of two spaces, one with skew symmetric form, another with symmetric bilinear form, again has a skew symmetric bilinear form, and so we can consider this symplectic group. And certainly there is an embedding of SL2, which is just SP of V, and SP of V times orthogonal group of F hat certainly embeds into this big symplectic group for four-dimensional. Now, this orthogonal group, or maybe special orthogonal, I don't know. So SO of F check just identifies with the so-called circle. So F hat 1, set of elements X, such that x bar is x to the power 2 plus 1 is 1. Well, it's also the norm of x, meaning no norm from this quadratic extension to the ground field. Okay, and so what we actually had here was rather a special orthogonal group, SP of V times F hat 1 embeds in SPW. And now this group is abelian because, well, it's just a circle, one-dimensional, and its representations are very well known. They're just characters. Okay. On the other hand, somehow our good luck was as follows, that the Andreev representation on functions on lambda, and this lambda was a two-dimensional Lagrangian subspace, and it was the tensor product of just one line in this two-dimensional space V with F hat. So this V representation is very small. This can be given some formal mathematical definition, but for our purposes, it means that its restriction to this product, SP of V times F hat 1, has the simple spectrum. So it decomposes for example, if we decompose it according to one group, then the multiplicities certainly are representations of the other group, and they're irreducible. Okay, that's the simple spectrum. In principle, there could be higher multiplicities, bigger, but in this case, they're all just irreducibles. So it's direct sum over all characters of this circle. Like this. Well, if you wish tensor eta, so as a representation, it's one-dimensional representation of this circle times some representation of this group, but it turns. I hate this. I don't know how to do it. But it's irreducible. Irreducible representation of SPV. We just computed the dimension. To prove this last time, we computed the dimension. Well, and it was Q minus 1. Maybe there was one exception that in some particular case it split into two irreducible representations of dimension Q minus 1 over 2, but apart from this small exception, it's just this. And there we are. Okay, so in this way, well, at least in the end, it will turn out that we construct all the Caspidal representation of SL2. All the Caspidal representations of SL2 arise this way. So it was somehow a great success. And this method of construction is very widely used in representation theory. So there are many more examples like this. So, well, just this paradigm. You have one big group. In this big group, you have product of two smaller groups, and you have some small representation of this big group. When you restrict it to this product, it gives a so-called model. So it decomposes in direct sum of products of reducible representations, and this way you get a bijection between representations of one group and representations of another group. Okay. So in this case, one group was abelian, so its representations were very easy, and we used them to classify the Caspidal representation of the other group, which otherwise are very hard to construct. Okay, but in more general situations, both groups are non-commutative. Both groups are not easy to classify their irreducible representations, but anyway, you get some bijection between representations of one group and the other group. And say, certainly you've heard about the famous Langlands program, and somehow, whenever people succeed in proving this Langlands reciprocity, it's just the same way. So you can say you want some correspondence between representations of whatever, Adeli group and the Gloa group. and you make them both act somewhere in a cohomology of some moduli space of Stukas, and then this gives you the desired correspondence. So this cohomology of moduli space of Stukas decomposes as a direct sum of tensor products for irreducibles. And this way you have a correspondence between irreducibles of one group and the other group. Okay, so this is a very important construction of bijection between representations of various groups. Okay, so this was it, but if I am back in March and we continue our studies, then the next set of exercise will be sort of a toy model of this. So we can, instead of f hat, we can consider just the two-dimensional vector space with a split quadratic form. So that hyperbolic, bilinear form. Well, say x1, y1. I want to pair it with x2, y2. And this will be x1, y2 plus x2, y1. Okay. If I wrote minus, I would obtain this symplectic form, but this way it is a symmetric form, but hyperbolic split. Okay. Now I wonder what is SO of F2. It's a question to you. Say, Ivan. What is the group of automorphisms of F2 that preserve this form of determinant 1? At least maybe you can guess some transformations which do preserve this form. For example, the quadratic form Q of xy is just xy. Maybe over 2 I should write, but it doesn't matter. So which transformations preserve this form, quadratic form? What can you do with xy? Well, yes? Huh? Just speak up. Certainly what you say must be true, but just speak up. Yes. Yes. So it's just F Q star. So xy goes to Cx, C inverse y. You can also swap them, but this will have determinant -1. So if I am about special orthogonal group, it's just this. Okay? And so this way, you just repeat the whole thing again. SP of V times SO of F squared will embed into SP of W, where W is the direct product, V tensor F squared. F is FQ, yeah, as before. Thank you. And just repeat again. You can take C lambda and restrict it to this product, FQ star. Okay. And now again, this is a commutative group, so we only have its characters. And so it will be direct sum over all characters. Maybe now let me write it whatever. Xi, a character of Q star over C of lambda Xi, tensor Xi. Okay, and now let's compute the dimension here. So the dimension there was Q minus 1. What will be the dimension of the eigenspace here? Vladislav? So how did we argue last time? The circle had Q plus 1 elements upstairs, yes? Up there. And lambda had Q squared points. It was two-dimensional Lagrangian subspace. But certainly our functions vanish at the origin. So yeah, if they have non-trivial character behavior, they vanish at the origin. So essentially we have Q squared minus 1 points. And then we take the orbit of this of this group of Q plus 1 elements. So each orbit has Q minus 1 elements. And that's why the dimension was. There are Q minus 1 orbits of this Q plus 1 dimension, Q plus 1 cardinality group. Okay? And this time it's vice versa, because this group has Q minus 1 elements. And so the dimension will be Q plus 1. Okay? And so does it give you a hint at what you get? What will it be? So it will be some representation of the group SPV, it is SL2, before we get these mysterious Caspillar representations, and now you get Q plus 1 dimensional. Yes, it's just principal series. So it's induction from Borel in SL2 to SL2 of the character, well, sort of Xi inverse. Okay? And this will be your problem in the next home assignment in March already. Okay, but somehow there is no choice. Nothing else could happen. So you will eventually prove it, but nothing else could possibly happen. And in this way, you see that somehow the principal series and the Caspillar representations are, from this point of view, very similar. They just correspond to two forms of SO2. There is this split form of SO2, just a multiplicative group, and there is this non-split form of SO2, the circle. Like over real numbers, also you can have either dilations, R star, or the real circle. Okay? The same way, over a finite field, there are just two forms of SO2. Well, this very representation gives rise via this model construction to Caspidal series if you use the non-split form, and to the principal series if you use the split form. Okay? Somehow, just from the point of view of dimension, here is Q minus 1, here is Q plus 1, so they're very similar. We will later on say compute the whole characters, not just the value, the identity, the dimension, but the characters everywhere. And you will also see that they are very similar. In a sense, that they are like analytic continuation. And the same phenomenon you can observe also for real or p-adic groups. So though the actual construction of a discrete series and principal series are very different, but the final results, say for characters, is very similar. And this is somehow one of the great mysteries of representation theory, not fully understood till nowadays, but well, that's how it appears. Okay, so now maybe let's recap what we did last time. Last time I claimed that first of all, the restriction of this representation, say C of lambda eta. So now we're back to this cuspidal case. Forget about this toy model till March. And when restricted to the Borel subgroup, in SL2 can be given by explicit formulas that extend to the Borel subgroup in GL2. Okay. Well, to this end, we have to extend eta from the unit circle to the whole multiplicative group, eta tilde. Sorry. Okay. So we extend this multiplicative character to the multiplicative group of the quadratic extension, and then we say that A alpha beta 0 delta f of x is eta tilde of delta psi over beta delta inverse x f over alpha delta inverse x. Okay. Now, what else did we say last time? We said that the whole of GL2 is generated by the Borel subgroup. And the unique matrix, I always forget where is negative 1 here. 0, 1, negative 1, 0. Okay, and now this Borel contains the mirabolic subgroup A, B, 0, 1. And when we restrict any cuspidal representation of GL2 or SL2, but SL2 does not contain this subgroup, so we better stick to GL2. Any cuspidal restricted to P always looks the same. It's just pi. This pi was the induced representation from the unipotent subgroup 2P of a non-trivial additive character. Okay, so our representation, all the representations we construct, all those guys and extended, well, maybe let me call it C of lambda, eta tilde, so to say. When we receive to the merabolic subgroup, it looks the same, and we only have to write down how this matrix acts. Okay? At least in principle, it determines everything. Because the whole group is generated by this and that, we only have to write down how this matrix acts. Still, we'll have to do some work, but let me then introduce some notation. So J eta of U is 1 over Q, the sum over all elements with norm U, psi of T plus T bar, then eta tilde of T. So it was some notation. And then we proved last time, and the proof was very straightforward, namely from the general theory of Weyl representation. We know that this element 0, 1, negative 1, 0 acts by Fourier transform, and then we just rewrite Fourier transform explicitly in some coordinates. So the theorem we proved last time was stated as follows. So choose a section. So we have 1 goes to this unit circle, goes to the whole multiplicative group, and then the quotient is the multiplicative group of our ground field FQ. There's just the norm. Yeah, norm of T is T. T bar is T to the power Q plus 1. Okay, and we choose some section here. Yes. Then this identifies C of lambda eta with C of FQ star, and this is just the this pi. Okay, this induced representation was realized in the space of functions on multiplicative group. Well, maybe I should say not pi, but induced from U to pi psi, U to P. Okay, and then we set kappa, some intertwining operator, kappa f of x is f of Sx multiplied with eta tilde of Sx bar. Okay, and we also set rho f of y is the sum over all multiplicative group eta tilde inverse of x, j, this j, eta of yx, f of x. And then finally, the diagram commutes. So we have our functions, well, C of lambda, eta, then there is this intertwining operator, identifying with functions on FQ star. And here we have the Fourier transform. So the action of this matrix. And here we have this row. Okay, so in this way we explicitly describe this representation of cuspidal discrete series corresponding to the character eta. Okay, and now we have to classify all such representations. Namely, we have to prove that they all appear exactly once in the following sense. So we set eta bar of t is eta of t bar. Yeah. There is this involution on our circle. And then the GL2 modules C of lambda eta and C of lambda eta bar are isomorphic. Maybe maybe this about SL2 models actually, and for GL2 I need tildes like this. Okay, so let's prove this. Just looking at the explicit formulas here. So, for example, we can look at this formula for upper triangular and also at this formula for the Fourier transform. And what can we see if we look there? Well, for example, let's look at the Fourier transform, though it looks more scaring, but in fact it's even easier because you see here nothing will change. We sum up over some circle, not the unit circle, but other circle of radius u, so to say. And the conjugation preserves this circle. But the function psi is of t plus t bar, so it's always also conjugate invariant. So this does not change at all. Fine, but this will change slightly. And also in the formula for upper triangular, also eta tilde will change slightly. No, not slightly, but to the conjugate. But the point is that you see here we sum up over the elements not in the quadratic extension, but in the ground field. And there too, delta is in the ground field. So the point is that for x in the ground field, eta tilde bar of x is eta tilde of x. Why? Yeah, just because of conjugate, yeah. Because x to the power q is x. Okay, so no problem at all. So this is evident. And now, well, another lemma is that eta tilde bar is never equal to eta tilde. It's never self-conjugate. Why? Well, maybe under the assumption that eta is non-trivial. We start from some character of the unit circle, then we extend it to the whole multiplicative group of the quadratic extension. And if this original character was not trivial, then this extension is never self-conjugate. Why? Well, we just have to compute eta tilde of whatever, t over t bar over t. And what do we get? What is t bar over t? T bar is t to the power q. Yeah, so it's t to the power q minus 1. And we have this sequence. And what does this exact sequence tell us? What happens if we take arbitrary element in this group and take its q minus first power? What do we get? So we have f, well, f hat. And then we have this, I don't know, multiplication by q minus 1, yeah? Where do you get? No, it's quadratic extension. It's quadratic extension. So what's the kernel and what's the image? What's the kernel, first of all? Just from this. Which elements are self-conjugate? Ivan? Pardon me? Right. Just the embedding. And what's the quotient? Just say over complex numbers. Take complex number and divide it by its conjugate. Where do you land? In the usual complex plane. Z modulo Z divided by Z bar, where do you land? Try. What is the image of Z divided by Z bar? In the circle, right. Okay. So apart from this exact sequence, there is sort of dual exact sequence like this. So there the norm was taking power q plus 1. And here is power q minus 1. Okay? That's just the sort of say dual exact sequence. Okay. In particular, this is surjective. So if eta of t bar over t is identically equal to 1, then eta tilde restricted to the unit circle is just eta restricted to the unit circle, and is identically equal to 1. But we assume that it was not identically equal to 1. Okay? So there are no self-conjugate extended characters. Okay? And now finally we can prove another theorem. Yes? Just from these formulas, the explicit formulas, they coincide on the nose. For example, the upper formula, you replace eta tilde by eta tilde bar, right? But you only apply it to delta, which is in the ground field. But the ground field is invariant under conjugation. So nothing changes at all. Yeah? And then here, again, here I have some summation over elements in the ground field. So when I replace eta tilde by eta tilde bar, nothing changes, right? The only problem is with this J. But J is also written in such a form that when you replace eta by eta bar, nothing changes again. Yeah? So just explicit formulas show you that nothing changes. And then on this very blackboard, we had a toy model, yeah, for the principal series. And then please tell me, Mikhail, what does this lemma correspond to in the toy model? So now we just proved that the cuspidal series do not change when I conjugate my character. But what about principal series? What will be the analogous statement? That the principal series does not change when I do what? No, just swap. So the principal series for GL2 is given by two characters, right? mu1, mu2. And if I swap them, then representation is isomorphic to itself. We know this. Well, in your next set of exercises, you will have to prove this from this model construction. Fine. So now the theorem says that if the cuspidal representations eta and psi tilde are isomorphic, then, well, either eta tilde is equal to psi tilde, which is stupid and evident, or eta tilde is equal to psi tilde bar. And nothing else. So apart from this lemma, there are no more coincidences. Okay, let's prove this. So well, on P, they both coincide with this pi. Okay, which is irreducible. And so we know that for upper triangular matrices, they will just coincide. So for G equals, for example, 1, 0, 0, delta, but delta is in the ground field. We will have just from this explicit formula, yeah, on the upper blackboard, we will have eta tilde of delta times f of delta inverse y will be equal to psi tilde of delta times f of delta inverse y, and hence psi tilde of delta will be eta tilde of delta for any delta. Okay, let's just remember this for a while. Anyway, it's a good start. Already something is equal. But it's on the ground field. Yeah? Now we have to somehow understand what happens on the quadratic extension. Now we also have rho eta tilde equals rho psi tilde for the Fourier transforms, those rows. Yeah. So rho is the action of 0, 1, negative 1, 0. Okay, so what does it mean? It means that the sum over x, eta tilde of x inverse, j eta of yx, f of x is equal to the same thing with psi instead of eta. Okay, so since this is for any function f, it implies that j eta of u is equal to j psi of u, for any u in the ground field. And it in particular implies that the sum of over the bigger circle of radius u, psi of t plus t bar eta tilde of t equals the sum over the same circle of psi t plus t bar psi tilde of t. Okay, now take again some delta in the ground field and replace t with delta t. Then we get that the sum over t bar equals u, or maybe some other v, psi of delta t plus t bar, eta tilde of t equals the sum over t bar equals v, psi of delta times t plus t bar, psi tilde of t for any v and any delta, and it implies that the sum over t bar equals v, psi tilde of t plus psi tilde of t bar minus eta tilde of t minus eta tilde of t bar times psi of delta t plus t bar is 0, but this sum is certain modified sum, meaning summation over well, how to say, over well, in the sum we only choose one representative of any pair t bar and t bar t. Okay. Now what shall I erase? Sorry. Just one moment. Let me erase this. Okay, so given x in our ground field, we can find a t in the quadratic extension such that t plus t bar equals x and t times t bar equals v. Well, maybe. Right? How do we find it? Vladislav? but well, maybe they are surjective, each of them separately, but why they are surjective together? Yes? Right, right. As a solution, thank you, of the quadratic equation x squared minus xx plus v equals 0. Okay. Then ax, well, this is small x, xi tilde of t plus xi tilde of t bar minus eta tilde of t minus eta tilde of t bar is well defined. I mean, is independent of the choice of this x. Yeah? I mean, sorry, independent of the choice of this t. For given x, yeah, it's, well, if you swap t and t bar, nothing changes. And hence, the sum over all elements in the ground field, ax times psi of delta x is 0. Okay. And now, if x1 is not equal to x2, then the characters delta goes to psi over delta x1, and delta goes to psi of delta x2. Well, sorry, maybe I shouldn't say, no, maybe I shouldn't say this. Just the characters. Sorry. Like this. For all x in FQ are linearly independent, yes, yes, or just whatever. It's called, I think, Artin lemma. Or yeah, whatever. So for any finite abelian group, its characters are linearly independent. They form a basis in the function of the dual group, and that's why the Fourier transform works. And hence it means that ax is identically equal to 0, because there can be no such non-trivial linear combination. Okay, and so it means that xi tilde of t plus xi tilde of t bar is equal to a tilde of t plus eta tilde of t bar for any t in our ground field. Okay. Sorry, not in the ground field, in the extended field. Okay, and now recall this equality that works for the ground field. So we had this for the extended field and this for the ground field. So we also have this inequality, which means that psi tilde of t times psi tilde of t bar equals eta tilde of t, eta tilde of t bar. Yeah, we argued from this exact sequence, yeah? And so we're done. Again, by solutions of quadratic equation, so psi tilde of t and psi tilde of t bar is the same set as eta tilde of t and eta tilde of t bar. And we proved our theory. Okay, so we constructed as many Caspedal representations as we would expect. Yes?
In the last part, we proved that the action of matrix 0, 1, minus 1, 0 agrees.
Yes?
But why there agrees on
We
Barrows?
started from this. It was here.
But we showed that they...
So no. So wait. First, before in the lemma, we proved that if psi is tilde or tilde conjugate, sorry, if psi is eta or eta conjugate, then the formulas are the same. Now we started from, now this converse, the theorem is converse. So we assume that the representations are the same. In particular, the formulas are the same. And then we deduce that psi is either eta or eta conjugate. Okay, so we can start. Then in the beginning of March, we will compute the carriers, count the representations, and see that we constructed all of them. So, by the way, let's maybe say now how many we constructed. So there are q squared minus 1 characters altogether. Right? But yeah, divide by 2. But first we remove the self-conjugate ones. The self-conjugate ones never appear. So among those, there are such that the restriction to the circle is trivial. So how many do we remove? We remove q minus 1 because we have this exact sequence or whatever. I already raised another exact sequence. But if they are trivial on the circle, they factor through the norm. So there are q minus 1 of them. So we subtract q minus 1, and then we divide by 2. And so we get q squared minus q over 2. And to compare with, so that's how many Caspedals we have. To compare with, let's remember how many principal series did we have. So there were q minus 1 Steinbergs, and also some were irreducible. So how many irreducibles? We just have to choose 2 characters, but distinct. So, yes, absolutely right. Yes. So again, it's very similar. You see q minus 1 times q here and times q minus 2 there. So everything looks like members of the same family, in a sense. Fine. So at least we did construct very many cuspidal representations, and now we have only 10 minutes left. So let me say a few words about the Whittaker model. It will be very, very useful. So it is really a great instrument in representation theory. Unfortunately, we will not see it for general GLN, only for GL2. But it is actually always very useful for GLN and for any group at all. It's one of the most useful instruments. Oops. Sorry. Well, maybe already spoke about it. I mentioned it some time ago. So this is by definition the induced representation from the unipotent subgroup to GL2 of this character, or by the transitivity of induction, this is the same as the induction from the mirabolic subgroup of this Q-1 dimensional representation pi. Yeah. And then the theorem I want to state is that this Whittaker model psi is the direct sum of all higher dimensional representations. I don't know how to say it. V rho with multiplicity 1. Of all reps of dimension Q minus 1, Q plus 1, each with multiplicity 1. That's why it's so important. Okay, well, you did dismiss characters; they are trivial in a sense. Everything else you obtain just once, very conveniently, and the proof is immediate, just by the Frobenius reciprocity. We know that any non-character V rho is the direct sum of this, well, after you restrict it to P, is the direct sum of this induced representation. From P to G. Sorry, from U to P of psi plus the Jacquet functor of V. Jacquet functor of V is just the invariance or co-invariance of the unipotent subgroup. Okay, and that's it. So, and this occurs with multiplicity 1. So because of this, V will occur in this induction with multiplicity 1. Okay. So that's it. The proof is very simple. Well, modulo our work with Jacquet functors. Yeah. So the important thing is to know that any representation restricted to P contains this higher dimensional irreducible. But we did this a couple of weeks ago. Okay, and now the following corollary will be very much used in March. So for any non-character V row, well, there is an intertwining operator, an embedding. V into this induced representation, but induced representation is in functions. Okay, but these functions are, by definition, left U psi invariant. Okay, just the induced representation. And it's defined up to multiplication by a constant. Yeah, because the multiplicity of this V in this induced is 1. So the intertwining operator is just up to well defined up to dilation. Okay, what does it mean? It means, in other words, for any vector in our representation, there is a function, Whittaker function. WV from G to complex numbers, such that first it almost never vanishes. It's an embedding. Second, it's linear. CV1 plus C2V2 is C1 WV1 plus C2 WV2. Also, it is left U psi invariant. Okay, and finally, it is intertwining. So, row of H V at G is WV of GH. Okay, for any GH in our group. Okay, and well, they all span W row in the space of functions. W row 1 intersect W row 2 is trivial if row 1 is not row 2. Yeah, just because the whole thing splits as a direct sum. Okay, so this realization of any representation in functions on G is called the Whittaker model of this representation. Okay, and then we will study it in March, and in particular, it will allow us to write down explicit formulas for the character. And in your home assignment for February 28th, I wrote down those explicit formulas for all the characters. So there's principal series, Steinbergs and Caspitals. And for principal series is just the formula for the character of induced representation. Maybe you look it up somewhere or prove it yourself or whatever. But it is something very important, well known, and not difficult. Okay, so I assume that you can solve all the exercises, but the last one. The last one is the character of Caspidal representations, and this we will do in March. So that's it for February. And as I wrote, I am looking forward to your solutions. I will go to Japan tomorrow for 2 weeks, but I hope I will be able to receive your solutions and grade them. And you have assignments up to the end of February now. Thank you.